to lesson 8. We're working with trig applications. We're going to go through 3 different types, although with trigonometry there are like infinite uses of it. But we're going to look at 3 pretty specific types. The first are the classics, solving for sides. We've done this back in geometry, so these should be kind of familiar. Right? For example, we have a slide and a playground has a ladder that is 15 feet tall. If the angle the slide makes with the ladder is 52 degrees, how long is the slide to the nearest whole foot? Alright. These problems work really well with a picture. Right? Here's our ladder that's 15 feet tall. Our slide, we're not quite sure how long it is, but that's what we're trying to figure out. And we know, because we're working in trig, we're working with the right triangle. I'm going to put my 90 right here with the ladder. And they gave us one more piece of information. The ladder and the slide make a 52-degree angle. Now, what we've done in the past, we're going to continue to do now. We're going to label theta. So I'm going to change colors. From theta, we're going to identify the sides that they give us. They gave us adjacent and hypotenuse. So then we think about Sohcahtoa. This is using, looks like cosine. Cosine of 52 equals A, which is 15, over H, which we don't know. This is a 2-step problem. Multiply by X. And then divide by cosine of 52 degrees. Make sure that for this problem, our calculators are in degree mode. I'm using Decimos. I've mentioned that a lot of times. It's a really good program. So I want you to make sure when I click on this little wrench up here that we're in degree mode. Okay? And we're doing 15 divided by cosine of 52. And they tell us 24.3. But we want to round to the nearest whole foot, so that rounds to just 24 feet. That's not a bad slide ride. Yeah. 24 feet of pure joy. Okay. So you got one to try. This is just really a refresher, so this shouldn't be too difficult. Pause the video and resume when you want to check your solution. Alright, picture always helps with this, right? You are standing 50 feet away from a building. Here's the building, and you're this far, 50 feet. Here's our 90. It says that you have to look up to see the top of the building. And the angle that you're looking up at is 86 degrees. And then it mentions this little thing about your eyes are 4 feet above the ground. Why do we care about that? Because here's our actual triangle. From your eyes to the building is your 90. And then you have this gap 4 feet. So basically, whatever we find our height to be, which is what we're looking for, we're going to have to add on 4 feet to make up for our eye height. So, we're trying to look for this side. So, theta. Ooh, excuse me. We label the sides that they give us, right? They give us the adjacent and the opposite. So now we're thinking tan of 86 degrees equals O, which is X, over A, which is 50. 1-step problem here. Multiply tan of 86 by 50. And what the calculator ends up telling us, rounding properly, is 719 feet. That's a pretty tall building. Nope. So I just typed it in again. It actually says 715 feet. I knew I messed up a little bit there. I think I typed in 87 or something like that. But 715 feet. Hopefully you got that same answer. Oh, I know why. Because we have to add that 4 feet. That's why. Right? That 4 feet from our eye height, we have to add in. So we get 719 feet tall. That is the height of the building. Alright, so those are the classic trig applications. We're going to look at some kind of new stuff. One thing that we're going to look at to start with are called bearings. Now, bearings work actually with both boats, nautical, or with airplanes, which would be like aerial. Okay, they're slightly different, I guess. With airplanes, you use a fixed north line versus boats, they use a fixed north-south line. And if you notice our definition, a bearing is just the acute angle that a line of sight, so wherever we're looking, would make with a fixed north-south line. So we're going to look at a quick example of how these work. First, they're going to tell you which part of the north-south line to start from. So this example says start from south, and it wants us to head west 40 degrees. So I'm going to start from south and head west 40 degrees. So that would be our bearing. Okay, that's how that particular one works. And this green line is our line of sight. Okay, north 22 east, that means we start at north and we're going to go 22 degrees towards the east. Okay, so you have one to try on your own. Figure out where that line of sight would end up falling. You want to start from north, head west, 65 degrees. It's going to be kind of shallower, right about there. Okay, so that's how bearings work. What we're going to do now is work on a problem that involves boats leaving. And the reason why we're using boats is because, leaving docks, is because this is something that really happens. Nowadays, sure, we have GPSs and that type of stuff, but we still have issues where boats get lost. And we can calculate roughly where they should be by just using a little bit of trig and those bearings. So this is something that is still done to this day. Even with all the technology, people can still calculate this type of stuff. Okay, so let's do this out. And by the way, a picture is going to help a lot. In fact, we're going to draw 2 pictures for this one. Okay, it says that the ship leaves dock and heads west 8 miles. Then it turns south 35 west for 11 miles. We want to find the ship's bearing and distance from the dock to the nearest hundredth. This would be miles. Why? Because it's giving us an idea of where we would need to look for this boat if we ever needed to look for it. Okay, so here's the dock. And it said that that boat left in the west direction. Right? It went this way, west, for 8 miles. And then all of a sudden, it turned south. So here's our south line, right? North would be up here. This is south. 35 towards the west. So from here, we're starting to turn this way 35 degrees. And then they traveled that way for 11 miles. Alright, so here's the deal. What they're looking for, and I'm going to draw it in a different color completely, is they're looking for this distance from the dock to wherever they were right here. And they're looking for this angle, kind of. Really what they're looking for is the bearing, which would be from this south line the angle here. Okay, so this is what we're really looking for. Now, there's some good news because if we notice west versus south, that's a perfect 90. So once we get this angle, we can subtract from 90 to get the bearing. So that's good news. We have a game plan for the bearing part. The distance part right here, well, in the past with trig, we've needed to have a right triangle. And this does not look like a right triangle. But good news, we can actually figure out this piece because we have some information about this angle and this side, right? They said that this angle was 35. Well, if I was to draw in the rest of this triangle right here, I have a 90, a right angle, and I can figure out that this angle measure right here, the inside, is actually 55 degrees, right? Because it's 90 being formed with south and west. Subtract 35 down here, and we got 55. Okay, well, why is that useful? Well, because now look at this pink triangle, right? From here to here, and this 8 right here that we used before, now we have a right triangle. So if I can figure out the length here and here, I can use a Pythagorean theorem, and I can get the distance that we need. Right, so there's now a game plan for everything we need. From here, we're given the hypotenuse as 11. We need the opposite side, and we need the adjacent side as well. So I actually have two things I need to do. I need to do O and H, which is sine. So O over H, which is 11. And we need to do it for adjacent, which would be cosine. Cosine equals A over H. So by solving both of these, I will get missing parts to this overall right triangle. Okay, so we multiply by 11. 11 times sine of 55, we're in degree mode on a calculator. It ends up being 9.01, rounding to the hundredths. For this cosine, we multiply by 11. 11 cosine of 55, we get to be 6.31. Again, rounding to the hundredth. Now, what did we just find? Well, this was working with opposite, so over here we have 9.01. This was working with adjacent, so this strip right here is 6.31. Now let's make a much more complete picture for us to work with, because this is kind of jumbly, right? Here's what we really have. We have a length here that we found to be 9.01. Together, these two lengths, if we add, that becomes 14.31, right? The whole thing. And then we can start talking about finding the distance away from port, as well as finding the bearing, right? We want to know this angle here. But we can find out this angle inside by using trig inverses, right? So if I was to put theta and label these sides, I know we've got opposite and adjacent. That's working with tan, but I'm trying to find that angle. So we need tan inverse. Tan inverse of 9.01 divided by 14.31. Type that into the calculator, and they tell us 32.2 degrees. But that was this inside angle. The way that bearings work, it needs to start from the south and head towards our direction, which is west. So we already talked that all we have to do is subtract this from 90, because that's a right angle right here. Right, so we'll take 90, subtract 32.2, and we get 57.8. That's this angle right here. And we started south and headed west. So here's our bearings. South, 57.8 degrees west. Now we need to find the distance. Pythagorean theorem, right? A squared plus b squared equals c squared, the side that we're trying to find. Take the square root of both sides. This I can type in right into my calculator because the people who designed Desmos or Texas Instrument calculators or whatever you worked on, they worked pretty hard for you to be able to do this. I would say though that just a plain iPhone calculator, you can't type this in straight. You need an actual app. So anyways, you do that and it comes out to be roughly 16.91. That's after rounding, and we're talking about miles. So what did we just figure out? Here's the dock. This is where they started from. This is where they are right now, in the ocean or wherever, right? Maybe a giant lake. Okay, but this is where they are. We found their bearings, which is how anybody on the sea is going to be reading it, right? South, 57.8 west. So we know which direction to head, and we know roughly how far, 16.91 miles away. We should be pretty close, if we had that direction for that long, to finding them. Now that was quite a process, I'm not gonna lie. I got another one for you to try on your own, so you might need to rewind this video and watch that last one again. But however you do it, pause the video for this one and check your solutions when you're ready for it. Okay, let's see how you did. We drew a picture which really helped out, I think. All right, we started at port, which is just a dock, and it headed east. This time they were heading east for 34 kilometers. And then all of a sudden, they're turning north. So here's our north line. And east, which would be out this way. 50 degrees. And they only went for 8 miles. Oh, I'm sorry, not miles, kilometers. So what we're looking for is how far away from port to nearest hundredth. Okay, so that's this dotted line. And we want to find the bearing. So it's going to be from north heading east. And we need to figure out that angle. Remember, in the past we got the inside angle, so we need to subtract from 90 to get that. That also happened over here as well, right? Because in order to get all this information, we needed a complete triangle to work with. So 90 minus the 50, which was our bearings, gives us 40 degrees in here. And now we have this little triangle to work with. We have a hypotenuse of 8. If I want to know my opposite, that means we're working with sine of 40 equals O over H, which is 8. And if we want the adjacent side, it's basically the same thing, just with cosine. These are both one step, right? Multiplied by 8. So you type in 8 sine of 40 on your calculator, and you get approximately 5.14. Same thing with this, right? 8 times cosine of 40, and you get approximately 6.13. So we just found the adjacent side and the opposite side. Okay, so now we're going to redraw what we know. By the way, at this point, I'm hoping that you're checking, did we get those solutions, right? These two together, 34 and 6.13, is 40.13. This height we found to be 5.14. So we can find the bearing first. This would be opposite and adjacent from theta. And we know whatever we find here, we're going to have to subtract from 90. So we're working with tan inverse of 5.14 divided by 40.13. And you type that in, it's going to be roughly 7.30. Now, that's this angle. We need the bearing. That would be from north heading east, and we're going to subtract this from 90. 90 minus 7.30, that comes out to be 82.70. 82.7 degrees. So here's our bearing, north, 82.7 east. Hope you get that one. Then we want the distance. Distance is going to be a squared plus b squared. So 40.13 squared plus 5.14 squared equals c squared, our hypotenuse. So we take the root, and we find our hypotenuse to be approximately 40.46 kilometers. So you have to go in the direction north 82.7 east for 40.46 miles, and you'll get to where those people are. I told you we had 3 types of applications. Here's the last type. These are completely different because we're not going to have a triangle to work with. What we're working with now is something called simple harmonic motion. I got a real quick story about this, right? When I was in college, I got an award in school, and my father and mother came to watch this, award ceremony. And the doctor who was talking at the time was talking about simple harmonic motion. And wouldn't you know it, you look over, and my dad is snoring super loud during this award ceremony. So that's how I always remember simple harmonic motions, because my dad fell asleep during a presentation about it. Anyways, these are kind of cool. There's lots of stuff that you can work with. It's any kind of repetitive motion, which would be vibrations, like snoring, bouncing, like a basketball, which we're going to see an example, rolling waves in the ocean, rotating wheels or pedals, all sorts of stuff like that, right? So here's how simple harmonic motion works. D is going to be the distance from the origin at rest at time t. The distance from origin is going to be equal to A, which will be amplitude, times sine of Wt. Okay? Or we can use cosine. But what's important is that our W value has to be positive, and it's going to be the angular frequency. Okay, well, what does that all mean? Well, we've got certain things that are happening here, right? We've got amplitude, which is just the max displacement from that average line, which we saw back when we were graphing our functions. You have a period, which is 2 pi over W, and you have frequency, which is W over 2 pi. Frequency with the number of cycles per second. So they're either going to have to give us this angular frequency, or they're going to have to give us a period, and we're going to have to find that W. But everything that we need is really pretty much given to us. You'll see an example right now. They ask us to write an equation for the simple harmonic motion of a piston that has a max displacement of 12 inches in a period of 2 seconds, and we want to find the frequency. So a piston, by the way, is just something that moves up and then back down, kind of like in an engine. You would have the explosion in the engine compartment, and it would cause a piston to move up and down, and that's what makes the engine really move. Okay, so we're working with D equaling A. We'll just work with sine. You could use cosine, it doesn't really matter, of Wt. Well, some things they give us, right? They give us max displacement, which is amplitude of 12. So we can replace A with 12. What we need is W. Well, if you remember, we said period equals 2 pi over W, which is something we need. And they gave us a period, right? They said 2 seconds. So I'm going to replace P with 2. So we've got 2 equals 2 pi over W. Now I can actually start solving. Multiply by W, and then divide by 2. We end up getting just plain old pi. So pi t. And that's our equation. Yeah, that's the function. So if I wanted to know a distance, I would just have to plug in the time, like maybe 4 seconds, and I could figure out how far this thing has traveled. Now, they also ask for the frequency. Well, frequency is W over 2 pi. We already knew what W was. It was pi. We divide that by 2 pi. Those cancel out, and we get 1/2. What does that mean? That means that every second, half a cycle is complete. So it takes 2 seconds for a cycle to be complete, which makes sense because that's what our period is. Those were the things that they were looking for. Not bad, right? So here's one for you to try on your own. This one involves something bouncing. Same kind of simple harmonic motion. Alright, let's check out how you did with this problem. We've got a ball being dribbled by a basketball player. It's telling us the max displacement of the ball is 2 feet. Now, before I even finish the problem, just for those of you who are like, what's going on here? Okay, here's our basketball player. They're bouncing this basketball, right? And it says max displacement. So think, this ball's going down and hitting the ground, and then it's bouncing back up to the person's hand, right? Here's their hand, and then it's going to be bounced back down, and then it'll go back up, right? So it's going to have this kind of motion to it. And it's telling us that the max displacement is 2 feet. So what's really happening is this person's dribbling the ball really high up. They're bouncing it like 4 feet above the ground. And they're slamming it back down so it goes up a full 4 feet. That's what's happening. Anyways, so we want D to equal, well, that's our max displacement is 2. I like working with sine. You could use cosine. It doesn't really matter. But we need W. Well, they said that the period is half a second. So we got 1/2 equaling 2 pi over W. I'm going to multiply by W on both sides, and then multiply by 2. So we get 4 pi over W. Okay, just plug that into that equation. That's where it needs to go. 4 pi times T. That's our equation. Not bad, right? Then we want the frequency, which all we have to do is take this and divide it by 2. 2 pi rather, right? So 4 pi divided by 2 pi. Our pi's cancel. 4 divided by 2 is 2. So every 2 seconds we get a dribble. Oh, did I mess up slightly on this? I think I might have. Very slightly. No, that's correct. 2 dribbles per second. Right, so he bounces it and it hits the ground twice per second. Bounce per second. Okay. We're having one more type of problem that has to do with harmonic motion. Right, and this is how these ones work. Okay, now they're giving us an equation to work with, and they're going to ask us some questions about it. So we just have to extrapolate the information from the equation, basically. Right here they say an ocean wave can be modeled with the equation d equals 13 times sine of pi over 6t feet per second. Okay, so there's a wave in the ocean that has an average height from that average line of 13 feet. So basically, here's the wave traveling in the ocean like this, okay? And this height right here is 13 feet, okay? That's actually not that bad. I mean, ocean waves can be that tall. People surf waves certainly that size, so this is realistic enough, right? What they want to know is the max height, which we got right here. That was from 13. So the max height, which is also max displacement, is 13 feet. What else is happening? Well, we have a period of pi over 6, right? So every pi over 6, we get another wave. Okay, that is W, right? They want to know frequency, which we know frequency is W divided by 2 pi. Alright, I can simplify that. I'm going to pretend that that's over 1. So we got pi over 6 times 1 over 2 pi. My pi's are going to cancel out. My 6 and my 2 will multiply. So frequency is 1/12. What does that mean? It means that every 1/12 of a second, a wave is passing by. So that's actually really fast. This is like a hurricane kind of speeds coming at you. Or maybe a boat traveling by. Could be possible. Anyways, here's one for you to try. You're working with a pedal on a bike. So pause the video and resume when you're ready to check your answers. Alright, so here's what's going on. Think of this as your bike pedal, right? As you spin around and around and around, the height of that pedal is going like this, right? The height. Okay, that's why circular motions like that, wheels, are harmonic. Okay, and they gave us some information. They said that the average is going to be 4 inches. That makes sense, right? That means it's a 4-inch pedal. Okay, so they want to know the period in frequency. Period is equal to 2 pi divided by W, which they gave us as 10 pi. So if I divide by pi and reduce, we get a period of 1/5. What does that mean? That means in 1/5 of a second, this guy is pedaling, or girl is pedaling, a complete circle. Right? It goes like that, and then went all the way around in 1/5 of a second. That means for frequency, 1/5 divided by 2 pi, which would be 1/5 times 1 over 2 pi. That means, oops, I goofed a little bit, sorry. For frequency, rather, we want to be doing this number, 10 pi, divided by 2 pi. We divide by the pi's, the 10 divided by 2 is 5. So every 1/5 of a second you complete one pedal. That means every 5 pedals per second. I know I didn't say that right in the end, but I think you get the point, right? If you can spin this around once in 1/5 of a second, then in 1 full second you should be able to go around 5 times. What is that telling you? This guy is pedaling really fast, right? 5 full pedals per second. Maybe they're going uphill or something. But this is what they were looking for, the period and the frequency. Hopefully you got those. I know that was a long lesson, but those are just some of the many applications that you would use trig for. And hopefully it wasn't too confusing. I know the bearings can be kind of tough. If you're in class and you want to ask some questions about them, I will be more than happy to answer them there. As far as a simple harmonic motion, really it's just knowing what each variable stands for and how to get them. So leave your questions in the comment sections or bring with you to class would be even better. Until we meet in chapter 5, have a good one.